We're doing, where are we? I don't know. We're someplace.
Classroom.
We're in the classroom? So in chapter 21, and we're starting with problem number 27. It's 7:45 in the morning?
7:46.
It says I've got a 2N5484, which probably is irrelevant to the problem. It's just, just garbage there. So GMO is somewhere between 3,000 and 6,000 microsiemens. Now, why don't we write this as 3 to 6 millisiemens? Wouldn't that be better? I mean, why do I have to write it 3,000 to 5,000? Probably because some engineer decided to do it that way. VG to F off can run from 0.3 to 3 volts. Okay, determine the range of GM. Let's see, GM was selling for $2 a share, and now it's up to about 10, I think. So that the range would be 8. No, that's not what we want. Okay, so we want to find the range of GM, given that VGS is minus 12. No, minus 0.2. Minus 0.2 volts. So that being the case, we need a formula. So we have to go looking for it.
Hey, you made it.
Okay, so I'm on page 721. So on page 721, and I see that GM is GMO 1 minus VGS over VGS off. All right, so that being the case, I want to find the biggest GM I've got and the littlest GM I got. What is GM?
Manager.
The value of the transconductance at a specific point. So this guy's got some characteristic curve that looks like this, and at any specific point there's a GM associated with the slope of the curve, which turns out to be the transconductance by being the resistance. Why is it the transconductance by being the resistance? Well, if I had a curve that was voltage by current, then V is equal to IR, and now I'd have resistance as the slope of whatever it is curve I've got. But because I have IV, then my slope is going to be not resistance, but conductance. And that's why we call it transconductance, because it changes as I move up and down the curve. All right, so those are just English things. All right, so back to what we're doing. We want to find the maximum and minimum guy. That goes up and down. Okay, so we'll find GM, and we'll go with 3,000 microsiemens. 1 minus can go 3 to 6 millisiemens. If I go 3 millisiemens divided by minus 0.3, I think that's going to get the smallest that I could possibly have. And then if I look at 6,000 microsiemens, 1 minus no. This is volts. VGS is 2. VGS off is 0.2 volts, minus 0.3 volts. That should get my smallest one. 3 volts divided by 0.2 volts. That should give me my biggest one. Alright, so now it's time for calculator time. 3,000 microsiemen times, parentheses, 1 minus, minus 0.3 minus 0.2. Wrong pen. Where'd my pen go? Well, it looks like that's 1,000, 15,000. Looks like that's 15,000 microsiemen. No, it's not. Yeah, it is. No, it's not. Yeah, it is. No, it's not. No, it's 1,500 microsiemen. All right, that looks good. And then we'll do the guy down below. 6,000 microsiemen time 1 minus, this is a minus sign down here. Minus, minus, we just put in plus signs. All right, so minus, oh, I hope not. 3, then I'd have to do it all over again. That'd be such a pain. Alright, so I look back at my where did my formula go? There's my VGS on top, VGS off on the bottom. VGS off, oh yeah. Now you tell me. Alright. Alright, so we want a 0.2 volts on top with a minus sign. Alright, now we have to reconsider what we're doing. To have this guy be the smallest, we'd want the minus 3 to be there and the minus 0.3 to be here, right? If I could make a minus 0.3. Okay, so now I'm set again. Alright, starting all over from scratch. Minus 6, oh, way to go. 3,000 double E minus 6 times parentheses 1 minus 2/3. I could have just put times 1/3 in there and been perfectly happy. 1,000 microsiemen. I'm going to do it again. No, we're not. That's wrong. 100. I bet you it's 100 microsiemen. What do you think? 100, because there's no point there. It's 0.2 divided by 3. No, that can't be right either. All right. Is it 2,800? I'll do it again. 3,000, not doing anything else with a bunch of fingers. 1 minus 0.2 divided by 3. Yeah, 2,800. Yeah. 2,800 microsiemen. All right, now 6,000 double E minus 6 times parentheses 1 minus 0.2 divided by 0.3. 2,000 microsiemen. All right, so now we're hosed. Yeah, yeah. So now we're going to have to put the 6 up here. So if we put the 6 up there and the 3 down here, then That'll be okay because we'll just cut this by 2 and make it 1.
So the
And then we'll
2,000 goes
double
with
this
6,000
one.
top.
We'll double this guy. 54 or 52? Was that 26?
No, it's not
28? 56. All right, we'll change that to a 6 and this to a 3. Okay, there we go. I think I like that answer better. Well, that was good. Did I waste enough time on that one? Are we on schedule for using the whole hour and a half on 4 problems? So, pretty much. 39. Maybe I should do it in multi-sim. What do you think? Number 39. Determine AV, the voltage gain, the Z in and the Z out, and 2164. All right, so I got 20 volts. I got 2 resistors. 9.1 meg. You gotta be kidding me. 4.7 meg. Where did they find those? And then I got this guy coming up to there, coming down that way. 470. And then I got a capacitor and 15k ohms. All right. So, and I got GM is the transconductance 2,500 microsiemen. Okay, so I got a 4.0 for drawing the picture. Now, is it possible to build it in multi-sim and get these answers? That's the real issue. And the answer is maybe we could do that. So I need to find R little d. That's what I need to do. So where's my equation for R little d?
The second one, I got 1,000.
There we go. So on page 730. So I'm looking at page 730. And for the circuit that I have, which is the guy on the top, I find that R big D, I need R little d. No, that's right. R big D. Okay, so on R big D, and that's RD in parallel with RL, 470 ohms in parallel with 15k ohms. All right, so I got my calculator out, and it's turned on, so that's good. Okay, so 1 divided by 470 plus 1 divided by 15 with 3 zeros, close parentheses, boom, 456 ohms. 456 ohms. I find that my voltage gain, I could spell voltage gain. My voltage gain is GMRD. All right, so what's GM? 2500 microsiemen times 456. .14. That's a lousy voltage gain. Alright, so that's all I got, 1.14. Now I want Z in. Impedance in. Okay, I'm looking at page 730 again. I see that impedance in is R1 in parallel with R2. And so that'd be 9.1 meg in parallel with 4.7 meg. And we'll guess that the answer is 3.2 meg ohms. Okay. Oh, I guess I should put it in my calculator too, right? Okay. 1 divided by, open parentheses, 1 divided by 9.1 plus 1 divided by 4.7. And my answer is 3.1. Oh, bummer. Missed it again. 3.1 meg ohms. Okay, so that's our second answer. Zn. And then we want, for our third answer, we want Z out. And we find on page 730 again that my Z out is RD 1 over YGS. And now we got to go figure out what YGS is because I don't have any YGS. So,
You guys speak up that thing. Everyone's saying I'm crazy. You really hear it. My brother here is crazy. I'm with you, man. Still don't know what you're talking about, so. Yeah, I don't know that. No, somewhat music, they play the app or quiet speaker. It's the voices in your head, dude. Don't listen. Don't give me that in a second. I don't think so.
The guy's saying I've heard all day.
That's kind of what I was thinking.
You get to get on my head.
How's that
Pull it
kid?
down a little bit.
now, I would imagine that we're supposed to go to the data sheet for the transistor. There is no transistor. What the heck is YGS?
Actually, until 11.
Isn't the amplifier a common drain, which would just be 1 over GM parallel R?
Did you find it in the book?
On 730,
730, yeah.
the amplifier that we're looking at isn't a common drain.
Oh, right.
Z out is just R as
Yeah.
parallel 1 over GM.
Or GM, right.
GM.
All right, so I was using the wrong guy, is what you're telling me.
I prefer shooting.
So that means I have to go back and redo that other guy too, right? So RD is 470, so 470
Around billion.
in parallel with 1 over 2500.
What are you gonna do? Beatbox?
All right, so I've got 1.
Fucking Louis.
1 divided by parentheses, 1 divided by 470
That would be like sumo wrestling.
plus.
William would try to find a way to
Plus.
get into a rap battle.
This is going to be 1 over 1 over, right? So that just should be 2,500 micro.
Yeah, that's what I got.
Yeah. Plus 2,500 double E minus 6. 216. But now we got to go back up to A, because I was supposed to use RS divided by RS plus 1 over GM for my voltage gain, and I didn't.
No!
So I'm supposed to be using RS divided by RS plus 1 over GM. And
I got behind, so
then I have to calculate what little RS is. Oh, bummer.
the RS is, gonna be 470 and parallel with 50. Cause it's, RS and parallel with
Well, is that what it is, an R?
That's what RD is. Oh, okay, gotcha. So that's going to be, I already calculated it, I just didn't know I did. This is really RS and not RD like I said it was. Okay, so this is going to be 456 divided by 456 plus 1 over 25 microsiemen. And okay, yes, I just put it in 156 divided by parentheses 456 plus 1 divided by 2500 double E minus 6 close parentheses equals, well, that's even worse. 0.53. 0.53. That's not much of a gain. I'm gonna put it in my calculator again because I don't like that answer. 456 divided by parentheses 456 plus 1 divided by 2500 double E minus 6 close parentheses. Boom. Yep, got the same answer. Must be true. Okay. So 39 is done.
What?
I mean, what?
Slow down, can you please?
Well, I'm trying to go slow. I think, yeah. Lunch is in it for another hour.
Oh,
All right, now.
Nowadays.
I don't get much easier. Back into work.
All right. I don't have control of that. Oh, my pen's upside down. All right, now, here is the, that's the fiscal year 12 federal budget. Okay, this is the fiscal year 13 budget. And the world's going to end because we only spend that much instead of spending this much. Right? The sequester is going to happen. The world's going to end on the sequester, right? And it doesn't even cut the amount of federal spending. It only cuts the rate of increase by a little bit, by all of 2%. And the world's going to end. Yeah. I think it's time that all the bums be thrown out. I really do. Because obviously we have too many lawyers in Washington and not enough real people.
I agree.
Yeah, because obviously there's something wrong with the situation. What is it? There's 100 people that are in the military that have retired and are getting more than $100,000. There are 10,000 people in the federal government that have retired that are giving $150,000 or more in retirement.
What?
That's bull.
Yeah. And
They don't do shit anyways.
For my taxes.
well, they're going to have to take your guns away because over your dead bodies as you take back the White House. But other than that, no. Yeah.
They're getting my guns.
Yeah. When when my dad was alive, he had guns in the house. So he had a 38 fully loaded and a white sock next to his bed with grandchildren playing in the house, right? You know, he had a Mauser hanging up that was left over from World War II. When he died, I told my brother, get the guns out of Mom's house, right? She's not. First of all, she doesn't know how to use them. Second of all, she wouldn't. And third of all, you're just going to have one of the grandkids get hurt, you know, the way we have it now. So he may have gotten all of them, and he probably did. And I'm telling this story to my mom at Christmas time. Dad died 15 years ago now. But I was telling it to my mom at Christmas time, and Mom said, well, that's not true. Oh, yeah? What part? Well, in high school, I was in the gun club. I shot guns all the time. Yeah, because when she was in high school in World War II,
Right.
the general population had guns. Why did the Japanese not invade the west coast of the United States? Because every single one of those asshole Americans have a gun. Yeah. Now that wasn't true, but that's what they thought. That's what they thought.
Well, you have a Japanese general that owed that actually.
Yeah. But and that's all it takes, just thinking that, you know. Especially on the West Coast, every household. And you can't have an army, you know. All right, back to problem number 51. I hope this one goes more smoothly than the last one.
I hope you do. I hope you get only 4 minutes apiece.
51. All right, so we have an enhanced MOSFET. All right. So that means it has a slightly different operating curve. And we have a VGS Thevenin. That might be threshold. 1 volt. And we have an ID on 8 milliamps. And is V still equal to IR? Yes, it is. So it should be pretty simple.
ID what?
Okay, we want to know ID on. And at VGS equal to 4 volts, we want to find ID. In fact, we want to find ID, the current at the drain, in 4 different spots for VGS at 1 volt, 4 volts, and 5 volts. So there's 1, 2, 3, 4 answers. Okay, so now we got to find an enhancement mode MOSFET. So there's a DMOS, there's a DMOS, and now I'm on the enhancement mode guy, and I find an equation on page 737 that says ID is equal to K VGS minus VGS threshold, or Thevenin. Sorry, Thevenin. Nope, threshold. I was right. Wow. Squared. And I have a formula for K. which says K is equal to ID on divided by VGS on minus VGS threshold squared. All right, so
Threshold.
yeah. Okay, so it looks like what's VGS on? VG31. VGS threshold so now we need a VGS on. Okay, so VGS on is 4 volts. VGS on is 4 volts. So I'm going to calculate K first. K is equal to ID on (2 milliamps) divided by 4 volts minus 3 volts squared. Well, that's good. I like that. So that's 2 milliamps. All right. So now I'm going to calculate ID 3 different times.
So equals 2 million.
All right. So I'm going to calculate ID 3 different times.
I think you're looking at the numbers for 50.
Yeah, 51 is 1 volt. VGST,
Threshold is 1 volt.
It's 1 volt, yeah.
Darn.
ID on is 8 million.
So I was looking at the wrong problem.
Right, well, yeah.
Okay, so we're doing 51. So that's 8 milliamps. And this guy is 1 volt. And we're squaring it? Yeah, we're squaring it. All right, so I liked it better the other way because I could do it in my head. 3 squared is 9. So that's 8/9 of a milliamp. All right, so 80 on is going to be 8/9 of a milliamp. 8/9 of a milliamp. 8/9 of a milliamp times VGS minus VGS threshold squared. So we're supposed to do it at 1 volt minus 1 squared. We're supposed to do it at 3 volts minus 1 squared. And we're supposed to do it at 4 volts minus 1 squared. That looks like a 0 milliamps. That looks like 2 squared is 4. 4 times 8 is 32/9 of a milliamp. And this looks like 8 milliamps. Okay, now we're going to move back just a little bit. Okay, so this is VGS is 1 volt, VGS is 3 volts, VGS is 4 volts. Okay, good enough? Do you want me to change the the 32/9 to something. Oh, it's fine the way it is? Okay. One more problem, then we have to do the test or go to lunch. We'll vote on it when we get the last problem done. Wonder which way it's gonna go. Oh, looks like this is a real bummer here. Oh, yeah, oh my goodness, look at the headache. I don't believe it. 59. I mean, I can't even draw the picture. The bias circuit shown in 21.7 is a current source biaser. Determine how the circuit obtains a stable value of ID.
What'd you say?
Okay, so anybody have the answer to 59 yet?
Highest steady voltage.
What?
Highest steady voltage.
I'm leaning towards I have no idea. Are there answers in the back of the book? Not for this one?
I don't think for this one there is. Oh, wait a minute.
This is sort of like
There
it
is answers in the back of the book.
for 59.
Oh, no, 57 is the last one they give an answer for.
Typical.
We're in 21, right? Yeah.
How the circuit obtains a stable ID.
Oh, I know, but I never looked, so I guess I never looked. Well, that's why I never knew, so I had to look at it.
Did you know there was every 48? Yeah.
Oh, did you? I never. Apparently that went over. With this presentation.
Well, I think I got it. I think the headache is the migraine is going away. Clarity of thought is coming back. If I had 18 volts and I sent it to some voltage divider thingy to a transistor, and this guy was 43K, and this guy was 24K, then what's the voltage on the base? Voltage on the base, 18, 43 divided by 24 plus 43. .5 volts. Well, what's the condition of that transistor? It's on, right? It's not off, it's on. Okay, so now that it's on, what is the maximum current that can be flowing in the circuit? So if it's on, then I've got a 0.7 voltage drop across that diode thingy, right? And so I got 18 minus 0.7 divided by 2.4K plus 4.7K. And so my current at the drain, 18 minus 0.7 divided by 2.4 milliamps. And that's how because this transistor, the bipolar transistor is on, that's what's providing the stable drain current. Now, as I change my signal going into this guy, I'm going to change the characteristic of that signal, but my drain current's always going to be stable. It's not going to be moving around. Was that enough BS for you? Yeah. Want me to see if I can find the study guide for the chapter, whatever it is, test?
Yes.
We'll see if we can find it.
Yeah.
Fucking hilarious. The one was trying to, it's about.
Oh.
His dad got busted in embezzling a bunch of shit, and she lost all her money. Her dad was prison, so she went to 4 streets pretty much. And last night, she went to her transfer firm and looking at her transfer case. And she went to her aunt to borrow money.
I was talking about the song, and
Hey,
I
first
was
time
talking about
she
that,
said no, she went back to
Starbucks
Starbucks
commercial.
her aunt's always
The guy.
she lives way younger than what she is, and she has her face. Do you have some morphine lollipops? And she's going, boom, boom. It was hilarious. And then you just said it and kind of go funny. It was even funny if you didn't even watch it. So. Yeah. So do you, but we don't tell everybody about that, do we?
Well, she's
We're not talking about you suck.
I know.
I don't tell everybody you are. I did now, but that's because you asked me to.
I just said you let my secret out.
You want some 2011 or 2013?
Well, it looks like I've got, there we go, chapter 19 to 21 study guide. Excellent. No. Good. I have no answers, so that's good. A PNP transistor with a beta of 350 and current at the collector of 60 milliamps. The base current IB is. What's 60 divided by 350? 60 divided by 350. So that would be Bravo. Yeah. Okay, so we'll go in and we'll grab this. All right. So we'll go with B. The function of DC biasing is to set the initial operating point, to saturate the transistor, to set the minimum operating point, to set the maximum operating point. A. The bipolar junction transistor is a voltage control device, current control device, heat control device, thermal control device. Okay, so is it a voltage control or is it a current control? C, current control is correct. With regard to transistor operation, VCC is the voltage measured across the base to emitter, the collector supply voltage, the emitter supply voltage, the DC voltage measured across the collector terminals. Bravo. Right.
Is this gonna be like last test, but the questions were not even close to being like this one.
I hope so. I'd hate to give away all the answers. With regard to a transistor amplifier, a graph that represents the possible combination of IC and VCC is known as the DC load line
I think it's probably, yeah.
or the AC load line. Yeah, a transistor, a graph that represents every possible combination of AC, of IC and VCE is known as. I'm going to go with C.
Has to be BC because
Yeah.
they're capital subscript.
Yeah,
Right.
exactly. So it's not, that's right. Yeah. So that's why I would do that.
Yeah.
The slope of the DC load line is given, for a given circuit, determines collector current and base current, cutoff current and saturation current, cutoff voltage. What's cutoff current? Anybody know? Friggin' zero, right? Emitter current, and well, that leaves C. Cutoff voltage, saturation current. That's correct. C. The unit of measure for compliance of an amplifier is compliance. Compliance. Oh, I know. There's a glossary in the back of the book. Should I guess? No, I don't want to. I don't want to give you the wrong answer. Compliance: the maximum undistorted peak-to-peak output voltage. All right. Voltage. That's exactly what I was going to say too. Which is not a characteristic of a common emitter amplifier. Mid-range input and output impedance values. High power gain, high range values and voltage of current gain. Okay, it can't be C. Mid-range values for voltage and current gain. Can't be D. I think I'm going to go with A on that one. Oh, maybe not. Maybe I don't like A.
Ooh, that is wrong.
Yeah. Common emitter. High range values for voltage and current. Okay, it can't be C. And it can't be high power, so that's not it either. So it's either A or D. It's delta. Yeah, I think it's D. The type of distortion that is caused by driving the transistor close to cutoff.
A nonlinear distortion.
Yep, nonlinear, correct, D. Crossovers happens in the AB amplifier when I have two of them. And there's no such thing as a linear distortion. And I don't know what this notch distortion, I never heard of it. Well, I certainly hope that there's a problem we have to use our calculator on, really. The common emitter amplifier gets its name from the fact that its characteristics fit all the common. No, that's garbage. The output voltage is always the same phase. Well, that's true, but that's not how it gets its name. It is the most popular kind. No. The emitter circuit is common to both sides. Okay, so D. A common gate amplifier. Common gate amplifier is characteristics by Bravo. High input impedance, low output impedance. All right, I'll go with B. Power MOSFETs can handle currents as high as.
Bravo.
Oh, I don't know. I'd go with the high one. I'd go all the way. Yeah, I can't think of any reason why it can't go to 70 amps or 1,000 amps for that matter. You think it's B? Yeah. The depletion mode MOSFET operates in the depletion mode, works very much like. No. The depletion mode MOSFET in its depletion mode works very much like a JFET, I think. Yeah, I think I'd go with Bravo on that guy. Voltage divider is also known as universal biasing. When the emitter bias junction is reversed, the transistor is operating in. The emitter base is reversed. Yeah, that'd be cutoff.
Good.
As, let's see, a CSJFET amplifier has that, has that, has that. What is the voltage gain? That's a common.
Yeah, where's 16 go? Where's 16 go?
I don't know.
Yeah, what's 16?
You're missing 16?
Yes, sir.
Right there. I can see it. I guess you just have to do 16 by yourself. Oh. Some guys are just so.
Just gotta have it all, I know it.
I know, and I was just about ready to answer 17 too. A general amplifier has a gain. What is a general amplifier amplifier?
General.
Admirals, of course, yeah. All right, generals, yeah, definitely. As a gain of that, the input, what is the voltage out? All right, so voltage out, 700 times 2.8 microvolts equals. Well, it can't be that one because that's a retarded answer. And that one's way too high. You know, that one might not be too high. We're not going to throw that one out yet. We're going to use our calculator. 280 double E minus 6 times 700. All right, are we happy with B?
Yep.
All right, can I go to 17 now? Is it okay? Is it okay if I go to 17? All right. So, now luckily I just did these problems. So, voltage gain is RD times G, 1 over GM, right?
That's why. So when you say the first time, like why?
and RD is 5K in parallel with 10K. Okay, so 5K so this is 3.3K. So 3.3K times 350 double V minus 6. That can't be right. Huh. 11.7 D. Delta. The simplest type of transistor biasing. Simplest type. Collector base emitter voltage divider. Simplest type of transistor biasing is known as. See, I would have gone with self-biasing as being the simplest, but I don't see that one there. I'm going to come back to that one. You want Bravo? All right. I'm not so sure. That has 2 transistors in it. That has 2 resistors in it, and I can come up with only one. With regard to an amplifier, which is not a type of gain, resistance gain, right? Exactly. Which one of the following statements for a JFET is not true? Not true. Okay, so it is a voltage control device. Maximum channel flows when the source gate voltage is 0. That's true. The gate and channel materials must be the same material. That one's true. So B. The gate and the channel have to be different material. Okay, gentlemen, is that okay?
So we agreeing to 18 being Bravo or what?
18.
I don't know. I'd have to look it up.
Well, agree that 18 is not right.
No, it's not Bravo.
Yeah, I don't think it's Bravo.
I don't think it is either.
It's going to be Charlie.
That guy is a dumbass. I would do that on Charlie.
So, other biasing. Emitter bias.
Julian.
I?
India.
So on page 646, the advantage of the collector feedback bias. A simple circuit was relatively stable. So I think I would go with collector bias A.
A? What, A?
Yeah.
Yeah.
Yeah, that's what I'm thinking.
See, I told you, I was wrong.
That you've wrong?
What's the hardest? You can only be wrong once.
Some people
That's
have
what I
problems.
thought.
There isn't a hard one. They're all easy.
Golly.
Yeah.
I thought I'd get you on that
Are you
one.
doing a retest on the,